Welcome to all of you in this second part of this lecture series on corrosion in refinery. In the last part, at the last of that lecture, I told that many of the corrosion mechanism proceed by changing mechanical properties of material, and due to change of that mechanical properties of material, materials ultimately fails. So for better understanding of corrosion, it is necessary to understand mechanical properties of material. So in this part, we will first discuss some of the important mechanical properties of materials, and then we will discuss different types of material which we use in refinery. Now, so to start with, uh, see, in any solid material or solid body, what we find that it is made of different atoms and molecules, and atoms and molecules are arranged in a particular fashion. Now, each atoms or molecules is experiencing or experienced intermolecular forces between the surrounding molecules, and molecules are arranged in such a fashion that they gain a position of stable equilibrium. Now, if I am applying an external force over the body, so what will happen? The distance between the molecules will increase or change, and because of that, the molecules will not remain its a stable equilibrium. So what will happen? There will a restoring force appears inside the material, and that will try to uh, restore the original molecules arrangement, so that the molecules will come again to its stable equilibrium, and so body will ultimately regain its natural shape. Now, suppose if I am applying an external force over a material, and due to that, body is changing its natural shape, and because of that, there will be a restoring force developed inside the body. Now, if I remove that external force, and if the body regains its natural shape, when we remove the external force, then that type of body is called elastic body. Now, if the body completely regain its natural shape, then it's called perfectly elastic body, and if a body partially regain its natural shape, then it is called partially elastic body, and this property of a material is called elasticity. Now, if I am applying an external force, and because of that the material is getting deformed, and if I remove that external force, and after removal the body remain in the deformed state and does not even partially regain its original shape, then that type of body is called plastic body, and this property is called plasticity. So we now understand two important mechanical properties of material: elasticity and plasticity. Now, one important point is that every material experience plasticity after certain external forces. After a point when external forces uh, increases beyond an elastic limit. So we'll discuss about this. Now, the first question is how plasticity arises inside a material. Now, you see, in material science, uh, it and material science, a crystallographic defect or any irregularity inside the material or inside the lattice is called dislocation. So dislocation is a type of defects. So for example, if you consider this a lattice, so you'll find that there is an extra half of planes of atom inside this material. So there is a irregularity here, and so this is called a dislocation. Particularly it is called an edge dislocation. Now, if you apply shear stress over this material, so what we'll find, due to force in this direction, this half plane of atom will try to move in this direction, and due to external force in the lower half of plane in this direction, this half plane of atoms will try to move in this direction. So what will ultimately happen? The half plane of atoms in this half plane and half plane of atoms in this half plane, the bond between these two half planes will break, and a new bond between these half planes and these half of planes of atoms will forms. And ultimately what will happen, dislocation will move from this position to this position. So if you continue applying these shear stresses, so what will happen, the dislocation will keep moving, and ultimately will it will go at this position, and the shape of the body will change. So dislocation is a way by which atom inside the material move, and due to this movement of atom, plasticity arises. So now why I am discussing about this the mechanism of plasticity, because when we discuss about corrosion due to hydrogen, we will find that when corrosion occurs due to hydrogen, and we find that hydrogen atoms enters inside the materials, and they collect at this dislocation position, and due to this collection, the movement of dislocation disrupted, and materials property for of its plastic deformation loses. So material will not remain materials will not be having a plasticity when dislocation movement will disrupt. So we will discuss about its length. So that's why we just introduced the concept of plasticity due to dislocation movement. Now suppose, so we have discussed till now about two important properties, elasticity and plasticity. Now suppose we have a material, this material, and I'm applying external forces in two opposite direction. So what will happen, if you take take a cross sectional area, you will find that the molecules in this half is experiencing a stretching force in this direction, and because of that the molecules in this half will try to pull the molecules in this half, so that it will so that the molecules will restore its natural position. And similarly the molecules in this half will apply a force in this direction, because the molecules in this half was experiencing a stretching force in this direction. So you'll find that the molecules of the two halves will pull each other, and this is called tensile stress. Similarly, there could be compressive stress, and when we apply tensile stress, and suppose due to tensile stress the material will deform and its length increases. Now this relative change of this length is called strain. So here strain will be delta L by L naught. So when you apply stress, there will be a strain. Now suppose I have a metal wire, and I am applying tensile stress, and due to this stress there will be strain, and I am plotting that stress and strain on this graph. Then what will find that initially a stress and a strain will be proportional, and if I remove that stress, the material will regain its natural shape, so the material will behave like elastic body. Now this will occur up to this point A, and this is called proportional limit. Now beyond this limit, a stress and a strain will not remain proportional, but still the material will behave elasticity. It behave like elastic body. It means that if I am stressing up to this point, and if I remove that stress, material will regain its natural shape. And there will a point come, that point B, when if I increase stress beyond this point, the material will not regain its natural shape, rather material will plastically deform. Now this point is called yield stress or yield point or yield strength, and below this yield stress material will behave like elastic body, and beyond this yield stress material will behave like plastic body, and material will permanently deform. Now if I increase my stress beyond this yield stress, what will happen, the material will plastically deform, but the deformation will be uniform. I mean, if the length of my material, the length of my wire is due to this stretching force is increasing, but the increase of the length is uniform, that uniformly diameter will thin throughout this length. Now there a stress come beyond that, this that uniform strain will not be there. Rather, what will happen, there will be localized stretching, and so this part will be experiencing much stretch compared to the other part. So what will happen, the thinning at this zone will be much higher, and so a neck will form. So ultimately what will happen, this neck will the thinning will material will increase, and a stress come where material will fracture, and so this stress is called breaking stress. Now this stress where the material was experiencing uniform strength is called ultimate tensile stress. So beyond this ultimate tensile stress, the material will experiences necking, and ultimately it will fracture. So you can see that any material after certain yield stress, that is beyond yield stress, will behave like plastic body. Now suppose if I am increasing my stress due to this strain is increasing, and my body is experiencing deformation after this elastic limit, and this deformation is very large. So that type of body is called ductile body or ductile material. So in ductility is basically a extent of plasticity. So if it is experiencing a high extent of plasticity, the material is called ductile. Now if I take this example, if the body is when I increase stress beyond the yield stress, the body is experiencing just little plasticity and it fracture very soon, then that type of material is called brittle material. So have we now have introduced another important property, that is called ductility and brittleness. So we now understand elasticity, plasticity, ductility, and brittleness. Now suppose if you take area under this stress and strain curve, and this was yield stress. Now this area under the curve is the energy per unit volume absorbed by material for before it's plastically deformed. So if you applying energy, then material will deform, but it will remain in elastic body, and this will be the energy per unit volume required for material to plastically deform. Now this is called resilience. And if you take sorry if you take the area under the whole curve, then that is called toughness. So toughness is the energy per unit volume required for a material to the energy per unit volume absorbed by a material before it fracture. So a tough material will require much high amount of energy before its fracture. So since this area is much less compared to this area, so generally toughness is related with plasticity, and resilience is related with elasticity. But in general, toughness is high, it means elasticity as well as plasticity, or rather elasticity as well as ductility is high. Now if you take this material, the area under the curve is less, so uh, the material will be less tougher. Okay, so there are other two properties, namely strength and hardness, which are important. Strength and hardness, these both properties are resistance of a material for permanent deformation, though, but they are different. There are difference in between these two properties. A strength is related with resistance for stretching, whereas hardness is related with local permanent deformation. For example, when we measure a strength, what we do, we stretch the material and we try to consider its ultimate tensile strength or yield strength. We are focusing over there, that whether this material is fracturing or not. Whereas when we measure hardness, then what we do, we press an indenter on material, and we uh, focus on how much depth the indenter is penetrating over the material. So it is a kind of resistance of local deformation or indentation or surface abrasion, whereas a strength is an ability of a material to withstand an applied load without any fracture. And whenever we talk about the strength, we usually consider it as ultimate tensile strength. Now, generally, when material strength increases, its hardness also increases, or vice versa. But it is not always in 100% cases. But for most of the cases which we will consider, strength and hardness will go parallel. And whenever hardness will increase, as a rule of thumb, you should remember that whenever hardness increases, material become brittle. Now, when we talk about carbon steel, we'll see here in this lower graph, what you will see that when carbon steel contain high amount of carbon, what you will find that is strength increases, but its ductility goes down, and because of that, is it can show a higher yield strength or ultimate tensile stress, and but it's a very brittle material. And when you reduce carbon at very low level, its strength decreases, yield stress or ultimate tensile strength is also lower, but its ductility is very high. And medium carbon steel is having better ductility as well as yield strength. So ultimately, area under the curve is high. So medium carbon steel will be toughest steel. When we'll discuss about different type of material which we use in refinery, we will talk about all these parameters in detail. But what we find, when carbon decreases, material weldability also increases. So there is two important parameter of a material: is hardenability and its weldability. Now, hardenability is and hardness are not synonym. Hardenability is not related with the highest hardness of a material which can it obtain. Rather, it is related with the depth or thickness over which a material can obtain its hardness. So if a material can be hardened at much deeper thickness, then its hardenability is higher. Now, when carbon increases, its hardness increases, also its hardenability also increases. But when carbon decreases, its or then its hardenability decreases and its weldability is increases, because then it will be easier to mold or something like this. So weldability increases. So what is written here, the hardenability of steel depends on its chemical composition, with greater quantities of carbon and other alloying elements, resulting in higher hardenability and lower weldability. So it means that when we increase carbon, we have two important properties we are gaining: strength, hardness, hardenability. And when we decrease carbon, we are getting two important properties: ductility and weldability. Now, weldability is mostly decided by carbon. That is the sole important alloying element in steel. But after carbon, chromium and vanadium is on second or third number. Copper and nickel is having very less significance on weldability. That's why we talk about equivalent carbon content when we talk about weldability. So till now we have talked about elasticity, plasticity, toughness, ductility, brittleness, strength, hardness, hardenability, and weldability. These are the most important mechanical properties. Now there is one another important mechanical property that is called creep. Now what happened when we keep a material at very high temperature for very long duration below its yield stress, then what we found that a material can permanently deform even below its yield stress if it is kept at very high temperature and for very long duration. Now this time dependent deformation of a stress component is known as creep. Now, this creep usually occurs in a hydrogen unit where reformer tubes or pigtails are at very high temperature, and when these units run for very long duration, then pigtail experience a creep problem. Like for example, this is the pigtail, and you see that this sagging is due to this creep. Now, to avoid this problem, what we use a material which is having very high creep strength. And generally, when we increase carbon, then its strength increases, its creep strength also increases. So we use high carbon grade steel for avoiding this creep problem. But there will be another problem at high temperature when you use creep high carbon, that is called sensitization. We will discuss at length about when we discuss about intergranular corrosion. But till now, for just for basic information, we can use high carbon steel. We will discuss about we should use a stabilized high carbon steel. And there is another material called heat resistance material. They are nothing but chromium and nickel alloys. They are having very high resistance of creep resistance. So when we discuss about materials, we will discuss about all those things. So creep is generally experienced in reformers. It can be also experienced in FCC reactor, where if it is used a hot wall type of reactor. We'll discuss about it. Okay. Now, uh, we have talked about different important mechanical properties. These are all the important mechanical properties. Now, if we there are different procedure by which mechanical properties of a material can be changed. One of these important procedure is called heat treatment. Now, heat treatment is basically heating of a material and then keeping the material at higher temperature for certain time, and that is called soaking time, and then cooling the material. Now, depending on at what rate you are heating or what rate you are cooling at, and what is the soaking time, there could be different techniques of heat treatment. There could be different types of heat treatment, like annealing could be, hardening could be, strengthening, tempering, quenching. These are all type of heat treatments by which we can change the mechanical properties of a material. Some of these treatment, actually what it does, it increases the hardness of material, whereas some of this treatment is what it does, it uh, increases the ductility of material. So we have heat treatment. Another way by which we can change mechanical property is called work hardening or cold hardening, where we do not need to go for very high temperature. Here what we do, we strand a material below its yield point, and because of this straining, plastic straining, it creates a new dislocation. And when dislocation creates, then dislocation density increases, and due to this high density of dislocation movement hindered. And because of this, material becomes hard, its plasticity goes down, and material becomes brittle. So there are many methods by which we can change the mechanical properties of material. One is called heat treatment, and another is called work hardening. Okay, let us now discuss about the types of materials which we use in refinery. Now, before I start discussion about this material, let us first briefly or very shortly go through this iron carbon phase diagram, which we use in steel manufacturing process. And here, what you see is at x-axis this is weight percentage of carbon, and at y-axis this is temperature. And what usually happens in a steel manufacturing process, iron and carbon composition remains at very high temperature in liquid phase, above around 1600 degrees Celsius. And suppose this composition is there, 0.5% carbon is there, and you are at here, and if you start cooling this steel, so what will happen, different solid phases appears. Now suppose if I am starting cooling from there here, so what will happen? First delta phase will appear, then austenite phase will appear. Austenite phase is nothing but a face centered cubic crystal lattice, and then if you further cool it, then a mixture of austenite plus ferrite phase will appear. Ferrite phase is having body centered cubic crystal lattice, and if you further cool, then austenite phase will convert into fully into ferrite phase, and depending on the composition of carbon, it could be also convert into cementite phase, which is having iron carbide Fe3C composition, or ferrite plus cementite, which is called perlite. So whatever the composition may be, there could be different phases when we cool it down. Now when still when this iron and carbon, the weight percent of carbon is below 2 weight percent, then that material is called steel, and if it is above 2 weight percent, then that material is called cast iron. So in this diagram, you can see that this austenite phase is not stable below 750 degrees Celsius. Below 750 degrees Celsius, when when we will cool it, then it will convert into either ferrite phase or cementite phase or perlite phase. So this is the just a brief understanding which is required for understanding of materials which we use in refinery. So in refinery, what we use is we use mostly steel for as a material of construction, and steel is, as we have just seen, that is a composed of iron and carbon, and which contains below 2% or below 1.5% carbon. And apart from this iron and carbon, they can also contain manganese, phosphorus, and sulfur as impurities. Now, this steel can be of three types. One is called carbon steel, and this carbon steel usually contains very less amount of other alloying elements apart from iron and carbons. And this carbon steel can also be of three type. One is called low carbon steel or mild steel, which contain carbon below 0.3%. Another is called medium carbon steel, which contains 0.3% to 0.6% carbon, and high carbon steel, which contains more than 0.6% carbon. And we have just discussed about that high carbon steel is having high strength and low ductility, whereas low carbon steel will having lower strength and high ductility and better weldability. Now, if apart from iron and carbon, if a steel contains other alloying elements, then that type of steel is called alloy steel. Now, it could be of chromium. Other alloying element could be of molybdenum or could be aluminum. Mostly chromium and molybdenum. Now, depending on the percentage of other alloying elements, alloy steel could be also different types. Like if it is containing 1% chromium and 0.5% molybdenum, it is called P1 type alloy steel. If it is containing 9% chromium and 1% moly, then it is P9. Similarly, it could be P11 or P22. P stands for pipe. If it is tube, then it will call T11, which is having 1.25% chromium and 0.5% moly. Similarly, T22, if it is tube, which is having 2.25% chromium and 1% moly. So this is about alloy steel, which contains maximum 9% chromium. Now in a steel, if chromium percentage increases above 10% or usually above 12%, then steel there is uh, a, a, a very high corrosion resistance arises in the steel, and steel usually do not corrode easily, and that type of steel is called a stainless steel because it do not get stain easily. So how it arises when chromium percentage increase above 12%. Some sources tell that above 10%, or some sources tell that 11% or 12%. So usually 10 to 12%. So if it is above 12%, then that steel is called a stainless steel. Now a stainless steel could be also of three types. One is called austenitic stainless steel, another is called ferritic stainless steel, and third one is called martinistic stainless steel. Now, see, we have just seen that this austenitic stainless steel basically contains austenite phase. Because of that, it's got name austenitic stainless steel, and we have just seen that austenite phase cannot be stable at room temperature. To make austenite phase stable at room temperature, what they do is they mix other alloying elements, which is austenite phase stabilizer. One of such alloying element is nickel. Now, if you add nickel above 8%, then that austenite phase will be stable, and it will be able to remain at lower temperature also. So that type of austenitic stainless steel, which is having austenite stabilizer nickel, that type of austenitic stainless steel is 300 series austenitic stainless steel. Like you have heard that SS304, SS316, these are austenitic stainless steel having nickel as austenite stabilizer. Okay. Now there are other alloying elements also, which is austenite stabilizer, like nitrogen or manganese. And if nitrogen and manganese has been added to make austenite phase stable, then that type of austenitic stainless steel is called 200 series austenitic stainless steel. So in refinery, 300 series austenitic stainless steel is more popular, so we will discuss about this only. So austenitic stainless steel is having more than 8% nickel. So generally 8 to 22% nickel, and also it contains more than 18% chromium. These are non-magnetic in nature, and they are non-heat treatable. Now what does it mean by non-heat treatable? uh, Here we understand by heat treatment that by heat treatment, austenite phase, if austenite phase can be converted into martensite phase, then that is called heat treatable. Means if any steel is converted into martensite phase by heat treatment, then that will considered as heat treatable. And because austenite contains very less amount of carbon, whereas martensitic phase contains high amount of carbon, so it cannot be converted by just cooling of austenite phase, and it won't convert into martensite phase, so it will always remain in austenitic phase only. So it is non-heat treatable. So by heat treatment we cannot convert austenitic stainless steel to martensitic stainless steel. They are non-magnetic in nature, and usually the most common is type 304, type 316, and type 317. Now there the first one is austenitic stainless. Now the second one is ferritic stainless steel. It does not contain nickel. Usually it contains 12 to 17% chromium, in some cases even more than 17% also, and it contains very low amount of carbon, uh, and other alloying element could also be there. And these steel is magnetic in nature, and they also cannot be heat treated. So by heat treatment it cannot be hardened, because ferritic stainless steel will always remain in ferritic phase in at a even higher temperature also. So, we cannot change its mechanical property by just heat treatment. So, though, but we can change its strength or hardness by cold working. Similarly, austenitic series mechanical strength can be changed by cold working. Now, third one is martinistic stainless steel. This also is having 400 series. So, a common example of ferritic stainless steel is SS 405, SS 409, 422 kind of thing. So it is a 400 series stainless steel. Now martinistic stainless steel is also 400 series steel. They contain slightly lesser chromium compared to ferritic stainless steel, and higher carbon compared to this ferritic stainless steel. These are also magnetic in nature, and this can be heat treated, so it can be hardened by heat treatment because it contains high amount of carbon, and when it heat it convert into austenite phase. So the heat treatment is possible here, and some of the example are SS403, SS410. These are representative of this group. So we can see that austenitic stainless steel is non-magnetic, ferritic is magnetic, and this martinistic is magnetic in nature. So if there are stainless steel and it is difficult to recognize which one is austenitic steel and which one is ferritic and martinistic, then we can use a magnet, and if it is attracting a magnet, so in that case it cannot be austenitic stainless steel because they are non-magnetic in nature. Now, apart from this steel, we also use heat resistant alloys. We have just discussed about this. They are having very high creep resistance. They can be used at very high temperature, above 1000 degrees Celsius. They are usually represented by H. The first letter will be H, and a second letter could be D, E, F, G, H, I, J, K, whatever, based on the composition. And they usually contains chromium, nickel, and iron. So for example, HK is a heat resistant alloy which contains 24 to 28% chromium and 18 to 22% nickel. Similarly, HT is a heat resistant alloy, contains 15 to 19% chromium and 33 to 37% nickel. Apart from these steels, some nickel alloy is also used in refinery. For example, Inconel is a nickel alloy which contains iron, chromium, and nickel. Iron usually below 10%, and rest are nickel and chromium. Hester alloy, apart from this iron, nickel, chromium, they also contains molybdenum. A significant amount of molybdenum they use in Hester alloy. Iron usually below 5%. Molybdenum could be as high as 25% or 30% maybe. And other is Monel. It only contains nickel and coppers, and nickel could be as high as 67%. And apart from nickel alloy, copper based alloy is also used in refinery, like Admiralty brass we use, where it contains zinc, copper, and a trace amount of tin, like 1% tin. And cupronickel. Now cupronickel and monel both are copper nickel alloy, but monel having higher amount of nickel and cupronickel having higher amount of copper. It could be 70% copper or 90% copper. And titanium alloys we also use. So this is all about the materials which we used in refinery. uh, this I have just introduced about the types of material which we use in refinery. This is just a basic introduction, and we will keep building our understanding about materials when we keep discussion about corrosion, because corrosion and materials are interlinked. A better understanding of corrosion required better understanding of materials, or vice versa. So we will keep building our understanding on this basic or basic understanding which I have just introduced in our subsequent lecture. So I'm going to stop here. Thank you.